Hello, everybody. So today we're going to be talking about how we can develop a fuller set of thermodynamic relationships for all of the various thermodynamic state variables that we've spent the semester developing. So in order to do this, we're going to go ahead and start with our good old friend, the internal energy, and building up a little bit more of a condensed set of equations to describe its behavior. So to do this, we can start with the first law of thermodynamics, which establishes that the internal energy of a system is going to be the same thing as the heat plus the work accomplished in the system. Now again, because internal energy is a state function, we can essentially establish any particular subset of our heat and work. So our classic choice here is reversible work and reversible heat. So one again can treat this as the maximum amount of work a system can accomplish and the minimum amount of heat needed to drive this reaction. Well, it turns out that we know that a reversible heat is the same as TdS, but we've also established that work is the same as negative P external dV. However, here's a wonderful little trick. Under reversible conditions, the external pressure is the same as the system pressure, which means with no assumptions of ideality, we're able to assert that any change in internal energy can be expressed in terms of a change of entropy and a change of volume. No approximations. And then this makes a really powerful equation. So much so that this is referred to as the fundamental equation of thermodynamics. And that we can actually do a lot with this equation to relate three of our major variables: the total internal energy inside of a system, the degree of order inside the system, and just simply the change of volume it occupies. Again, this makes a really powerful set of equations. However, we can also get a little bit more insight if we look at this almost through a calculus lens of viewing it in the differential form. Because from our classic multivariable calculus, we can essentially treat the internal energy as a function of entropy and volume. But this means that the prefactor for the entropy term is literally going to be the change in internal energy with entropy under isochoric conditions. Similarly, we see that for the volume term, it's going to be the change of internal energy with volume under isentropic conditions. Now, when we compare these two forms of the fundamental equation, a truly powerful set of expressions pops out, because it turns out that this means that the isochoric change of internal energy with entropy is simply the temperature. So by knowing the temperature of the system, we know how the internal energy changes with any change in entropy. Similarly, if I want to have an expression of how the internal energy changes with volume isentropically, well, it's simply as negative pressure. So if I know the pressure, I know the change in energy. And again, we also see a certain degree of logic with this. If I increase the order of the system, or increase the entropy of a system, I will see an increase of energy, and this is going to be much more magnified as we get to higher temperatures. But again, will always be a positive increase. Similarly, if I increase the volume, I'm always going to see a decrease in internal energy, because I'm going to be breaking bonds as long as I do so isentropically, and that essentially this is going to be related to the pressure, or more or less the concentration of the system. The more concentrated the system is, the more bonds I'm breaking. So we see a lot of logic and connection that's really founded in what we've established so far this semester. But it turns out that we can also use this equation to essentially develop other very similar equations. For example, we can use it to establish a similar expression for the Helmholtz free energy. Because we know that Helmholtz free energy is treated, the change in Helmholtz free energy is treated as the change in internal energy minus the change in temperature and entropy. So we established this earlier with our definition of Helmholtz. Now, this gets really nice as we insert the fundamental equation for internal energy into our Helmholtz. Because at this point, well, we have du minus pdv minus tds minus sdt. So by inserting this expression in for our du form, well, now we have two expressions for TDS, and you'll notice they're going to cancel out with opposite signs. So our Helmholtz has its own essentially fundamental equation where our Helmholtz free energy is going to change with temperature and volume. And similarly, we have an expression for how the Helmholtz free energy changes with temperature. And it turns out, ta-da, it has a dependence on entropy. So if I'm isochorically heating a system, I am going to see a decrease in the Helmholtz free energy, thus making the system more stable. And this is going to be a function of the entropy. The more entropy or disorder in the system, the more I'm essentially lowering increasing the favorability of the system, which again does make a large degree of sense. Similarly, we can apply the same logic for the change in Helmholtz free energy or favorability with volume if I make this change isothermally. And this expression is going to have a dependence on the pressure, where if I increase the volume of the system, I am going to see an increase in the favorability of the system, again, related to the pressure. With this negative term ensuring a more negative or favorable Helmholtz free energy. And again, this is going to essentially be due to an entropically driven process of letting the system spread out. And the more molecules I have, the more possible configurations my system can adopt. But again, we also have a lot of power in being able to express the variations of the Helmholtz free energy with temperature and volume, and it's very cool that their dependence relies on such simple and relatively easy to measure variables as entropy and pressure. But let's be honest, these equations are going to be most useful under isochoric conditions. And we're chemists, so it turns out we love isobaric conditions and state variables. So we are going to express this same set of relationships for enthalpy using a very similar process. So I know any change in enthalpy can be expressed as a change in internal energy plus the change in PV, which we can then split up into PdV and VdP. And then inserting our equation for the change in internal energy, we get TdS minus PdV plus PdV plus VdP. Yes, it's a bit of a tongue twister, but notice that the two PdV terms end up canceling out, which gives us, again, another simple fundamental equation, where any change in enthalpy is going to be expressed as a function of entropy and pressure. Where again, we see that if I increase the entropy of the system, I'm going to increase the enthalpy of the system, with again, this will happen as a function of temperature, because we have already seen a relationship in between ds and q, which is again mediated by temperature. Similarly, as I increase the pressure of the system, isentropically, I'm going to see an increase in the enthalpy of the system, as volume will always have to maintain a positive value. And again, the more volume the system occupies, the more the enthalpy will increase, with an equivalent increase in pressure. And again, we can repeat the same idea for the Gibbs free energy, because just like Helmholtz and internal energy were related by negative dTs, it turns out so is Gibbs and enthalpy. So we can again insert our equation for the enthalpy into our expression, and what we get is VdP plus TdS minus TdS minus SdT. So again, we see an elimination of our two TdS terms, leaving us with a simpler equation of VdP minus SdT. So again, this forms what's called the fundamental equation of chemical thermodynamics, as this is going to be the equation that's going to drive a lot of our work going forward, as we can express the change in Gibbs free energy, which again is going to be the change in energy available for chemical reactions, as a function of temperature and pressure. With again, if I see an increase in temperature, I'm going to see a decrease in, I'm going to see an increase in the favorability of the system. Again, for a pure chemical species, because entropy will always have to be positive for a pure chemical species. Similarly, if I see an increase in pressure, I'm going to see an increase in the Gibbs free energy, making the species less stable, which is again one of the reasons why it always takes work to increase the pressure applied to a system, or that the system exerts, because of this relationship in between pressure and free energy needing to always have a positive variable. And again, the larger the system, the more this expression ends up being spread out. And again, I do want to emphasize that as expressed, all of these variables are size extensive, but you can rephrase these four new set of fundamental relationships as indeed molar properties, where we'd have molar internal energy, molar volume, and molar entropy. And again, that would end up applying to molar enthalpy, molar Helmholtz, and molar Gibbs as well. So we now have four incredibly powerful thermodynamic equations. Unfortunately, this can be a bit of a handful to try and keep straight, especially with all of the negative signs floating around, and the fact that all four of these state functions are controlled by the same four variables. However, there is a convenient way to help remember it. And just remember that UG ship. So where at our four corners are our four variables, and at our sides are our four controlling thermodynamic functions. Helmholtz, internal energy, Gibbs, and enthalpy. And each of these functions is going to be controlled by the two variables next to it, with a constant of the two variables across from it. So let's go ahead and walk through a couple of these. So if I have, say, the internal energy, it's going to be the internal energy minus, because there's no arrow at this end, P dV, plus T ds. And congratulations, we just generated our fundamental equation. But we can also repeat the same process for Helmholtz, which is minus S dt minus P dV, again for Gibbs, plus V dP minus S dt. And again for enthalpy, plus V dP plus T ds. So again, using this relationship of our coefficients and our variables, we can express any of our four thermodynamic functions. And this gives us a huge set of thermodynamic functions that we can use to help explain a lot of chemical and physical properties. And we'll start applying some of the lessons from our fundamental equations next time. Until then, take care.